All right, welcome back to the SciMax channel. We're going to have a look at using Claude Code to try reproducing a complex optimization problem that is in this paper. My colleague Victor Alves showed me this paper, and if I scroll down to the main idea that we will look at today, it is this process. There's an evaporator, and we want to perform an optimization to minimize a cost that is defined up here, equation 31. And the equations for this are in the back at this appendix. So we have these 12 equations, and then there are some constraints that are in place that are defined here. And our goal will be to use Claude Code to extract the equations, the constraints, the variables, the conditions, and run the optimization and verify this profit, negative profit down here, $582.233 per hour. So that's the idea. Here's how we're going to do it. First, let me fire up Claude. And I'm going to tell it to use the optimization skill that I talked about before. And while that's running, I'm going to flip over here and tell you sort of the task at hand. So these are prompts that I'm going to use. I'm just going to paste them in one after another. We're going to first have Claude read the PDF, air quote read, and give it a goal. We're going to reproduce the analysis, and we don't want to solve it right away. We're going to go in steps so that we make sure that it does the right thing. And the first thing to do is review the variables in table 2, and then we'll use those in our analysis. So over here, I'm going to go ahead and press 2. We're always going to use the Python optimization skill, and the next thing we're going to do is to read this. And so Claude is already, guessing that we're in an evaporator example directory, and we want to explore this existing problem. So let's go ahead and say do this. Now, I've done a bunch of these, and I think it's important that I said do not solve this right away. Sometimes Claude gets ambitious and thinks that I want to do it right away, and I don't want to do it right away because the document has 9 pages. There are lots of equations, lots of numbers. We're going to want to make sure that we get the right equations, the right numbers. So it is first looking here. Here's the summary of variables in table 2. And there are lots of variables, some flows, some compositions. These are in percentages, some temperatures, pressures, some other things. And so now we have to tell it what to do next. Now, the next step is to get the equations. And I note here there are equations 38 through 49, and they're in Appendix A. And that's to orient Claude of which equations I want. Now, this is a video that I don't want to be terribly long, but I also hope ends up being correct. So it's a little bit tricky to get 12 equations and then verify that all 12 of them are right all at once. It is a little better if you do them one at a time and inspect each one. So we are going to still have a look at these, because if we don't get this part right, then nothing is right. So let's see how we can do this. We need to get to this appendix. Let me drag this a little bit over to the right. And we have, at steady state, note the time derivatives are set to 0. So for equation 38, we end up with f1 minus f4 minus f2 equals 0. That's good. Here we have f1x1 minus fx2. That's good. f4 minus f5. That's fine. This one is p2 x2 plus 48.43. What I'm really looking for as I go through this is to make sure that we don't have something like f2 where it should be f3. That happened in a previous example. And so we're just being careful because if we have the wrong equations, decimal in the wrong place, wrong variable, then we will not be able to reproduce it. So this one looks okay. Equation 44 looks okay. This one looks okay. Can't really see what I'm doing, but I'm looking at the equations. Equation 47. Also doing this a little faster than I normally would, just so it doesn't take so long. It's somewhat of an art to put these side by side and tell that everything is good. And then F5 is Q200 over 38.5. Okay, so that's good. Then it tells us 7 purely algebraic, 3 differential equations, total of 10 equations because of some key simplifications. All right, that looks like a good start. All right, now we need to get the constraints. That is part of the problem specification. And while that runs, let me scroll back up to the constraints, as we'll want to compare them. All right. So we have x2 is greater than, this is from the paper that it mentions it, 40, P2 80, P100 400, equation 35, 0, F200 400, sounds good. Equation 36, 0, F120, equation 37, 0, F3 100. All right, those are all okay. It does notice from the solution that is given in this table 2 up here that 2 of the constraints are active. We're not going to assume that. We are going to let the solver demonstrate it. So then we need the objective function. So let's put this in and scroll up to find that objective function that we need to compare, just to make sure we optimize the right thing. Look at it like this. So here again, I'm being specific, equation 31, and I'm asking it to show me and explain it so we can tell what we're doing. So we have, looks like it is already done. Let's scroll up here. Okay, here we go. J equals 600, F100, 0.6, that's good, good. That's good, and that's good. And then we want to minimize J, which is the same as maximizing the profit. Now, and then it gives some breakdown of what the terms are. Then this one, it's plugging in from the solution. So these two are kind of close. I think it is probably small difference due to rounding. So if we plug in their solution to the profit, we do get something that's quite close, but we're going to find some code that will generate that. Okay, so now we have to specify a few of these variables. So let's put this in. And here I'm going to ask it to explain the overall optimization problem, suggest a way to solve it, and explain why. Suggest the best way to solve it, and explain why. And then this is a sort of subtle point. It's a little bit of a preference. You can directly create the Jupyter Notebook, but having done this in other ways lots of times, I find using a Python script first is a good practice because Claude is quite capable of debugging Python scripts in a pretty tight iteration loop. And it's less good at doing that with Jupyter Notebooks. So let's see what we have. So we have an overall optimization problem to minimize this, subject to these constraints. This is in percent. This is in percent. We have degrees of freedom, available manipulated variables. 1, 2, 3, 4, 5. Remaining after the constraints. Consumed by the level control. Active constraints at the optimum. I think I need to see, okay. Let's say do not make any assumptions about constraints being active. I say that because I want to solve for x2 and find that x2 is at that active constraint instead of assuming it. Okay, let's go back and see what this says now. All right, 2 implementations, full space recommended, all variables are decisions. I like that. Model equations are equality constraints. I like that. You have an objective, a bunch of equality constraints that'll be zeros, inequality constraints. We set up an optimization using minimize, SLSQP, because we have both kinds of constraints. And I don't think it'll be a problem. And an alternative is that we do this, but there are some things that make it less recommended. So we'll just do the full space SQP, let the optimizer do its job. And after solving, we can inspect it to determine everything. I like that. The only thing I don't want to do is start with these values as the initial guess, because that is the solution. Okay, so let's say follow the recommended approach, but use a slight variation of the values in table 2 to make sure they converge back. Okay. This may already set up a notebook. I thought I asked it. Oh, I didn't. Right. This usually works. So Python scripts are usually like nice and tight. It writes a Python script, it runs a Python script, it gets text output. This is a large language model, and that cycle works really fast. What's challenging with the notebook is you have to open it to see what happens, and that's slow. And then it has to rewrite the whole notebook on each iteration. So I just find that iteration slow. And it usually works once I have a Python script to tell it to turn that Python script into a detailed notebook. And we'll see if we achieve that goal. All right, we're 15 minutes in and setting up a solution. Still looks like it's setting up a notebook structure, but there is a Python script. Let's just have a look real quick. It's fairly detailed. All right, so we import some stuff. We have some fixed variables, table 2 values, decision variable indexes, we have an objective, equality constraints. These things will all end up being 0. Inequality constraints, these are greater than or equal to 0. Initial guess is a small perturbation. Well, that's interesting. I would have thought this would just be random, but okay. Solve the optimization. All right, let's just go YOLO. See what happens. Now let's run this and see what happens. Many things have happened that range from it worked the first time to it finds a bug, has to fix it a few times. All right, let's see. We seem to have gotten to a solution. So we converged, maximum error, objective function, minus 582. That looks exactly like what is in there. We found the 2 constraints. This matches. We've got some degrees of freedom. And let's say use this solution to make a well-documented notebook, Jupyter notebook, complete with equations and analysis. Solution and analysis. Okay, while that's working, there's it's pretty impressive that it was able to do that. Let's come back over here and see what kind of things we created. We have this evaporator optimization.py. This is actual code. I can run it. And get all of the output that is in there. So we have our initial objective. Here's our current solution. These all match what is in table 2 to many decimal places. We have constraint verification, so it did a really nice job here doing the analysis. And the only thing this notebook is going to do is really provide a better looking artifact with all of the equations in it. We are close to 20 minutes in and pretty close to having a hopefully fully working solution, as long as the notebook actually has the same Python code in it. And it's worth thinking through, you know, what did we actually accomplish here? The equations were all in the paper. The solution was in the paper. The code was not in the paper. And so this was able to generate code that verifies a result in the paper, you know, quite quickly. And maybe this will be a starting point for a new study. You could do a sensitivity analysis. You might modify the equations for a different, you know, kind of reactor, different evaporator, etc. But one thing I think is interesting is this used to be like a class project scope. where you could probably take all day to figure out how to write those equations, how to code in the constraints, how to write out the objective function, pass it into minimize. By hand, this would be many hours of work in my experience, including debugging. And then you would get to this hard part, which is writing up a reasonable assignment. And it's not quite fair to say, we took what might be 6 months or a year of work that went into writing that paper and compressed it into 20 minutes. We definitely have not done that, even if we got to the same answer that they did. It's easy to get to an answer when you know how to get there. And the paper provided almost everything we needed to do that. So it's interesting to see, what can one learn about this? What did we learn by doing it? We have made Jupyter Notebook now. And here it is. So let's see, UV, run, Jupyter Lab. Let's just try this one. Drag it on over. So we have a nice table of contents. We have some imports. Looks like it's been run. Problem description, including some variables. We have some equations that we used that were transcribed. These are all going to be LaTeX, which is pretty nice. We have our optimization problem, including what these things mean, and some explanations, the constraints, the given disturbances, solution implementation, all of this. Let's go ahead and run these. I always like to run things and make sure nothing got made up. We have our constraints defined out here, inequality constraints, our initial guess. Starts out a little bit off. We set up the problem. This converged to minus 582, 233, exactly what we saw in the paper. Not that one. So down here, 582.233. And then there's some visualizations that you can see maybe are interesting. Some constraint verification, that's also good. Economic breakdown, fancy graphs that I would never make by hand. And more analysis than I would even consider doing by hand. This kind of stuff takes forever to fine tune and getting it exactly right. Sensitivities, we do have a little bit of warnings going on here. This is because we don't know how to print 100 in this subscript font. That's kind of not a big deal. And then some conclusions that are all down here, even a reference at the end. So really remarkable amount of work that went into making this. So I think that's pretty nice. This is not the first time I've tried to do this problem. This is the best that it has worked. I've probably tried 4 other variations that went off the rails in various ways that led to this particular one. So in the end, maybe it still took me half a day to work out in this vibe engineering approach. But I think this is a great example of things that are possible. Even earlier today, I found a paper, a friend gave me a paper on uncertainty quantification. I gave the paper to Claude Code, had it create a scikit-learn estimator, and was able to try out the new algorithm in under half an hour. So lots of new things in this space are coming as you learn how to use these tools. So with that, I'll close and see you next time. Thanks for listening.